All right, hello everyone. I'm not gonna lie, I'm super annoyed right now because I just spent the last hour and a half recording and I didn't press the unmute button. So, we're gonna try this again. Okay, so we're gonna go over the notes that have been posted for the first week. These videos are gonna be structured a little bit differently next week and thereafter. Parts of these notes that you'll see will be blank, and then we'll fill in the problems together. I think it'll be a little bit easier to absorb the material that way. But I want to make sure that this gets out before Friday, so pardon if it's not the best way to go through it, but just bear with me, okay? All right, so the notes that were posted online. So the first thing that we're learning in this class are functions. And functions are important because we need them to be able to mathematically model real-life problems. In this class, we're only going to be talking about real functions. Okay, so real functions, some of you have seen the symbol before. What I mean by real functions is the scalars or the types of numbers that are in the functions along with the variable are real numbers. So like integers, 2, -2, 1, 0, fractions, 1/2, -1/2. Irrationals are included, so numbers like pi, e, anything that's a real number. We're not going to be dealing things that are complex numbers, so I, which is equal to the square root of -1. We're not going to be dealing with those types of functions in this class. So for real functions, if we want to look at them, if we want to plot them, we do so on the Cartesian plane, it's called, where your horizontal axis or your x-axis tells you how your function moves left to right, or when you have shifts left to right, and this is for the independent variable. Okay, the dependent variable goes along the vertical axis or the y-axis, and this is for your up and down movement of a function. And sometimes in terms of vocabulary, we refer to the different parts of the Cartesian plane as quadrants. First quadrant, second quadrant, third quadrant, fourth quadrant. And this is convenient sometimes because you will know, for instance, that this is referring to the first quadrant, which corresponds to both your x and y values being positive. But my third quadrant refers to, for instance, your x and y values being negative. So it's just something that if you come across in a textbook, you just know roughly what it looks like. Okay, what they're referring to. And the position right here, by the way, the 0, 0, we refer to this as the origin. Now, the first type of function we're going to talk about in this class is the equation of a line, which has the form y is equal to mx plus b. Sometimes we also, instead of calling it y, we refer to it as f of x is equal to mx plus b. It's just a naming convention, but it means the same thing. In this equation, this m here, this refers to the slope of a line, so how steep it is. And the scalar part is your y-intercept. So if you had a line here, for instance, where we cross the y-axis, this is the y-intercept, this is our b. If you want to find out what the slope is, how steep this is, we can look to see that if I pick 2 points, say here and here, how much does the y direction change? And then how much does the x direction change? Sometimes these changes, we can write them as, the change in y over the change of x, or it's referred to as rise over run, which just means y2 minus y1, and then x2 minus x1, where if this point, we refer to it as x1, y1, and this point is referred to as x2, y2. All right, so this is how we would find the slope for this line. Now, a few different types of lines, if you will. So if your m is equal to 0, so in other words, you have a flat line, okay, something like this. This is referred to as a horizontal line. And in terms of writing out its equation or its expression, we write it as y is equal to constant, or if we wanted to, we could say f of x is equal to constant. So in this case, for example, I could refer to that blue line as f of x is equal to 1 if I wanted to. Okay, so these are horizontal lines. For vertical lines is when the slope is infinity. Now, if that's a little bit confusing to some of you, think about, for instance, if we took our 2 points here and here. They are at the same x point. So if I were to subtract them, x2 minus x1, they're the same value. So I could think about it as, x minus x, which is equal to 0. And if we have this part here, our denominator being 0, that means that m goes to infinity. It's a huge, huge number. Infinity is a concept. It's not a number, just as a little remark. But these things are called vertical lines. And we express them or write them out as y is equal to a constant. So for instance, this vertical line here is called x is equal to 1. This one is called x is equal to negative 1. And vertical lines are not actually examples of functions because they don't pass the vertical line test. Okay, compared to horizontal lines, if I take my pen here and drag it through, okay, I only hit if I take my pen and pull it down here, it only hits the blue line once and the green line once. But here, if I take my pen and pull it down, it's hitting the orange line nonstop. So this is not a function, this is a function. Okay, we also have parallel lines. Parallel lines are lines that never touch each other. And this is characterized by their slopes being the same. Okay, so if we were to draw a little triangle here and do rise over run, we would get the same answer. Perpendicular lines, however, okay, sometimes when they're drawn, people put these little squares there as well. This is when lines have a 90-degree angle with respect to each other. And we say that their slopes are negative reciprocals of one another. So if the slope of this green line, say, was 2, the negative reciprocal, I put 1 over whatever the number is, and then I put a negative there. So the slope of this one would be negative 1/2 if the slope of this one was 2. Okay, or more generally, slope m and slope negative 1 over m. All right, and here's just a little comment to what I was saying before. Sometimes instead of writing y is equal to mx plus b, we write f of x. Okay, so here are a few different problems, just to kind of refresh your memory a little bit. I know it's been a while since some of you have done math. So here's a problem where I just want you to tell me what the slope and the y-intercept of this equation is. Okay, this secretly is the equation of a line. How do I know that? Because I'm seeing an x, I'm seeing a y, and they're both to the power of 1. So I can rearrange them into the y is equal to mx plus b format. Now, how do I do that? Well, if I have this equation, I want to isolate my y. So I'm going to bring this term and this term onto my right side. Remember, when you bring something to the opposite side, you have to flip the sign, so positive becomes a negative. Because I have a negative in each term, they'll cancel out. We can divide out by -1. And then to isolate for my y, I just have to get rid of this 3. So I have to divide everything by 3. And now the expression of my line is in the form where I can very quickly tell, oh, this is my slope, this is my y-intercept. But this expression and this expression mean the same thing. They are equivalent. Okay, it's just easier to read and understand this one. Okay, let's do another problem. Slightly different this time. Find the equation of a line with slope 2. So I'm told what my slope is. And I know that it passes through the point 1, 2. Okay, so I need an equation y is equal to mx plus b, and I already know that I can put my 2 in here for my m, but I still do not know what b is. So, because I know what point the line goes through, or a point that the line goes through, remember that this is a point or a coordinate where the first part represents an x and the second part represents the y. So what I could do is I could plug my 1 into here and my 2 into here, and then I would be able to isolate for my b. Okay, so 2 goes here, 1 goes here, multiply it out, and now I just have b is equal to 0. So it's a line that passes through the origin, okay, because there's no shift, there's no plus b minus b, and we have y is equal to 2x. All right, let's do one now where we have to first find the slope. Okay, so let's say we want the equation of a line that passes through 2 points. You only need 2 points to find the expression of a line or to draw a line. So what we're going to do is we're going to refer to this as x1 and y1, and I'm going to refer to this point as x2, y2. It doesn't matter. If you wanted to call this one x1, y1, and then this one x2, y2, that's fine. Okay, it's not going to change the answer to the problem. Oh, that's another page. Okay, so first thing that we're going to do is find the slope. Okay, so what is our slope? We find it by using the equation rise over run, which means y2 minus y1 over x2 minus x1. And remember that we had our y2 as being 9, our x2 as being -4, and then we had our y1 being 6, and our x1 being -2. Okay, so 9 minus 6, this is 3. And then negative, careful about this now, -2, that becomes -4 plus 2, which is -2. So now we have our slope, so now it's kind of like our second example at this point. I know that I can replace my m with my -3/2. And I'm just going to pick my first point. You could pick the second point if you wanted to. Again, it's not going to change the answer to your question. Okay, so I'm just going to pick this one, and I'm going to put my -2 in here and my 6 into here. And then I get this solution. So the equation of my line ends up being, not what I've written down because I forgot my x, -3/2x plus 3. Okay. Now let's talk about parabolas. So now we're going to be talking about equations that have the form ax squared plus bx plus c. So I have a scalar or a constant term, a linear term, and now I'm adding a quadratic term or a squared term. A parabola in general is just a u-type function. It can either open upward like this, or it can open downward. And the point on the parabola where it is called the turning point or sometimes the vertex. It's where the parabola changes direction. So what I mean by that is if you look at this parabola, this is going downward and then it hits this point and then it starts going upward. Okay, that position is referred to as the vertex. Another way you can think about it is if I took a pair of scissors or I folded this graph along this line right here and I folded it like this, it is symmetric on the right side and the left side. So the blue lines would lie on top of each other if it was like a piece of paper and I folded it. This line is referred to as the line of symmetry. Okay? And one thing to just be careful of, a parabola is described as something with an x squared. So if a was equal to 0, this term would be gone and we would just have our bx plus c. This is the equation of our line. So a parabola, you may not have this term, you may not have this term, you may only have this term, but you have to have an x squared in there somewhere to be a parabola, and nothing higher than an x squared. If our a is greater than 0, our parabola opens upward, so like this. If a is negative, it opens downward like this. So similarly to when we were just doing the problem with the equation of a line, It's easy to quickly tell what my slope and my intercept is in this form. Not so easy to tell in this form. So for parabolas, it's a similar thing if you wanted to know, for example, what if this parabola had my vertex at the origin? What if it was shifted over 1 to the right, or shifted over 1 to the left? Or maybe it was moved upward. Sorry, maybe if it was moved upward by 1 or downward by 1. To quickly be able to tell if we have a shift along the x or y axis, we can look at, it's called vertex form. Some books call it general form, but I think vertex form is a little bit easier to remember or understand. And what is that? So that is if we write it like this. So parabolas have an x squared in them, but if you move in the x direction, left or right, this will tell you how you're moving. So what this minus h means is, let's say we have x minus 1 all squared. It means that I've shifted it 1 this way. If I've shifted it 2, I'm going to have x minus 2 in brackets and then all squared. If I move to the other direction, okay, say I move 1 over to the left, then I'm moving it to, there we go. I'm moving it to negative 1. So I would have x minus 1 all squared, so x plus 1. So when you move to the left, you don't see a minus here, you would see a plus. And then if you move in the y direction, either up or down, that's represented by the constant here. Just like the b-intercept tells you if you're up or down from the origin, similar to this k here. It tells you if you're shifted from the origin or not. Now, here's a little, here's a set of diagrams to help you more quickly understand or visualize what this expression means. So the standard parabola, the x squared, just looks like this. Vertex is at the origin. Now, what if I move it over this way by a certain amount? Let's say h. Okay, h could be 1, it could be 2, it could be 4. Let's say it's just some constant. Okay, so if I move it over h, then I would have to change the expression to be this, x minus h squared. If I moved it over to the left by h, so minus h, I'm going to change this minus to be a plus. Okay, if I am still centered at the origin, but if I shift my parabola upward, let's say by k could be 1, 2, 3, some number, then it's going to look like this. If I have a minus k, it means I'm going downward. Okay, so it'll look like this. And then maybe I'll have a situation where it's shifted both along the x and y axis. So you would get, my head's almost in the way, you would get this expression here. So I've gone over to the right by h and I've gone up by k. What happens if I went the other way? What happens if I went to the left and down, for example? So I would have x minus whatever that value is. Pardon the leaves. A little bit of ASMR in the background. Squared. And then I'm going downward, so I would have minus k. So I would have x plus h whole squared minus k. So that's if I wanted to go, somewhere down here, for example. Okay, so what I would recommend doing is just literally draw this out. Okay, when you draw it out, it may be easier to remember it. Now, to switch back and forth or to put something into vertex form, you can use a method called completing the square, but for those of you who don't know that method, there is a formula. So if you want to know what the x value is, or in other words, what that h is here, if your parabola is written in this form, you would take the constant term from the linear part, so b, and divide it by 2 times a, and then it would be negative. And then to find your k, you can, to find your k, you could then plug your h into here, because it corresponds to your x value, and then you would be able to get your k. Now, somebody asked me, where did these expressions come from? And we'll look at that separately. You won't be responsible for it because it's basically a proof, but we can talk about on Friday how exactly we got that. Could be a good exercise. So someone had asked me, where does this come from? If you take this expression and complete the square, you're going to end up getting your h and k to be this. And I'll write out a little thing to show you that. So say we do have a parabola in this form. So x squared minus 2x minus 3. And I want you to tell me what the vertex is, what the axis of symmetry is. So we can use these expressions here. So my a in this case is 1, my b in this case is -2, and then my c in this case is -3. So I can plug these into my formula, and I'm going to end up getting 1. And now, because I know I have my x is equal to 1, I just have to plug it back into that function. Okay, the x squared minus 2x minus 3. And if I do that, I'm going to end up getting -4. So that is my vertex point. So basically, our parabola is shifted 1 to the right and downward by 4. And the axis of symmetry is whatever that x value is. So if I write it in the general form, because, by the way, there's 1 in front of the x squared, there's not another number. The a in our case is just 1. And I know what the h is and I know what the k is. So this is the expression to easily be able to tell how my parabola, my standard parabola, is shifted. Okay, polynomials. So polynomials is just the generalization of what we're doing. So, the expression for a line is something called a linear polynomial, a degree 1 polynomial. A parabola is an example of a degree 2 polynomial or order 2 polynomial. So we can have cubic polynomials, we can have to the power of 4 as the highest degree, 5, 6, 7. So a polynomial is just an expression that looks like this, where you have a constant plus a constant times our variable to the power of 1. Maybe you'll have something with an x squared, and we just keep going and going until we get to some higher order term. And then depending on what this n is, we would say it's a polynomial of, degree n. So if the highest order was 5, we would say it's a 5th degree polynomial. Now, remember, these a's here, these are just representing some numbers, okay? 2, 3, a half, pi. They're constants or coefficients. Sometimes they're called scalars. We said that the largest exponent here is called the degree. So we would say this expression here is a polynomial of degree n. X is the variable, by the way. How do I know that? Because it's in the brackets here. And this thing right here, this p of x, this is just the name of the polynomial. Okay, we could have called it q of x, we could have called it z of x if we wanted to. It's just a name. And if we have an x that if you plug it in here, will make this all 0, this is what we call a solution or a 0 or a root. In other words, it's if you want to solve for x, that's what it means. It would give you p of x is equal to 0 if you plug that specific x into here. Mathematicians love polynomials because they can approximate any function. Yeah, this is really neat. If you had some crazy function, you can always approximate with a polynomial. It could be like a degree 100 polynomial, but they're very convenient for that reason. And here's just an example of some of the lower order polynomials. So a constant polynomial, linear, quadratic, and a cubic. So p of x is equal to 2, for example. That is a degree 0 polynomial. Q of y, notice that the names are different, and the variable is whatever's in brackets here. So that's why there's a y here instead of an x. Okay, don't let the naming convention trip you up. Whatever's in here is the variable, and that's why we have a y here. This polynomial now, I've named it L, where I've named the variable m. Okay, so I have an m squared here and an m squared here. You can rename it if you want to be an L of x is equal to 3x squared plus 2x plus 1. Again, it's just a naming convention. And then this is an example of a cubic polynomial where I've gone back to my variable x, because I'm also used to x. Properties of polynomials. So if you had two different polynomials, so same variable, okay, so we have an x here, we have an x here, but say I have a polynomial f and a polynomial g. They have different coefficients, okay, so different numbers, but the same variable. You can add them, you can subtract them, you can multiply them, and you can divide them. But in this class, we're not going to worry about dividing out polynomials, but it is possible, as I mentioned at the bottom of the page. But how do you add them? You just add the coefficients of like terms. So for the constant part, for example, I have a naught and b naught. If I add or subtract them, I'm going to have whatever the a naught number is plus or minus whatever the b naught number is. And then that is the new constant term for my polynomial. And then I have my x's, I have a1 and b1, and I would just add or subtract them together to get that new coefficient, so on and so forth. So you just add or subtract coefficients of the same order of x. Okay, like terms, sometimes they're called. For multiplication, I did this in general. Don't worry, you do not have to memorize this, but it's to show you that you have to distribute and multiply out each term. So this a naught, I'm going to have to distribute it to b naught, and then this term, and then the squared term, and then every term up until the nth term. And then I'm going to move over to this one and do it again. Distribute to the b naught, and then the b1x, the b2x squared, so on and so forth. Okay, and this is what dividing polynomials looks like, but again, we're not going to focus on that in this class, but it is possible. So just a couple of quick examples. So let's subtract two polynomials together. Okay, so notice this is actually a mistake. I didn't want these both to be 2, but that's fine. So here's a polynomial that could be simplified, and then here's another polynomial. This one has no x to the 9 terms, so this one is just going to be left alone. I have an x squared here, an x squared here, so that's 10x squared. I also have an x squared here. Careful about the minuses though. So I have 7x squared plus 3x squared plus 2x squared, so I have 12x squared. And then I have a constant term here and here, minus 1 minus positive 3, so minus 1 minus 3 to give me negative 4. This is a linear and a quadratic polynomial being multiplied together, where the linear one does not have a constant term. And we have to distribute this to each term. So I'm going to distribute this to here, and then distribute this to here. So I'll get 2x times x squared, and then 2x times 1 to be 2x. For linear and linear, you use something as sometimes it's referred to as FOIL, where you multiply the first parts together to get this, and then the outer parts together to get this, inner parts together to get this, and the last parts together to get this. So 4 terms. And then we have an x term and an x term, so we can combine them. So minus 2x plus 3x, so then there's 1x left over. And then I have this and this. We are going to be reviewing exponents, but remember that when you have to the power of something, it just means it's multiplying itself that many times. So if I have an x plus 1 cubed, now I'm having 3 linear terms or 3 linear polynomials all multiplied together. And you can multiply the first 2 together if you want, or you could multiply the second 2 together first. It doesn't matter because of BEDMAS. Okay, so I personally always just do it left from right. So I'm going to multiply this by doing FOIL. So this times this, this times this, this times this, and then this times this. I'm going to simplify it to get x squared plus 2x plus 1. And now I'm going to multiply it by this linear polynomial. So I have x squared times x, which is x cubed, plus x squared times 1, which is x squared. And now I move on to the next term and distribute to each one here. So 2x times x, which is 2x squared, 2x times 1, which is 2x. Move on to the next term, 1 times this and 1 times this, and then I get this expression. Please note though, okay, it's easy to sometimes make this mistake. This is not the same as this. Okay, just think about it for this example. this is not the same as x cubed plus 1 cubed. Okay, so just be a little bit careful about this. Now, how do we solve for x? How do we basically find these values where if you plug them into your polynomial, you get 0? These solutions or roots or zeros. And we do them by factoring or solving for x. So for linear polynomials, this is really easy to do because let's say we have, for example, px is equal to x minus 1. If I have this as being equal to 0, I can just isolate for my x. I get x is equal to 1. This is my solution. For something like a quadratic equation, if you can see that you can factor it, so I have an x, I have an x, I have a 1 here that's positive, but I have a negative 2 here that's negative. So because this is positive, and that has to do with the multiplication, I'm going to have a negative and negative, and now I need to pick numbers here and here that when I multiply them, I get this number, and when I add or subtract them, I get this number. So the factors of 1 are 1 and 1, and if I add negative 1 and negative 1 together, I get negative 2. So if you're comfortable with factoring, that's fine, but for parabolas or quadratic equations, you can always use the quadratic formula, which we'll review in one sec. But if this is equal to 0, and I have this, I can factor it, which tells me that x is equal to 1 and x is equal to 1. Now be careful, because when you see this, you may think, oh, the solution's x is negative 1. Not quite, not quite. Because remember, when you multiply two numbers together and you get 0, at least one of the numbers has to be 0. So this step here, what this means is x minus 1 is equal to 0, or in this case, x minus 1 is equal to 0. So when you isolate for your x, you get a 1. So just be careful about that. Now, we could use the quadratic equation, which says that if this is the general form of our polynomial of degree 2, then we can go minus b plus minus the root of b squared minus 4ac divided by 2a. And I like to put the divided by 2a out front. It's just a little bit cleaner for me to do it. If you want to go, divided by 2a here, that's also totally fine. And depending on what this actual number is, we can get different types of solutions. What I mean by that is, I'm going to make this a bit smaller so my head's not in the way. We can either get two solutions that are the same, kind of like this example. We got both solutions are x is equal to 1. And that would be if this term's not here, because we have a plus or minus, which means we have two cases. We have the case where I choose this to be plus and I choose this to be minus. So if that's 0, I'm going to get the same answer. If this is a positive number, then I'm going to get those two unique solutions. If this is negative, we get something called complex solutions. You would get complex numbers. You would get something with a negative value here, and the square root of -1, we refer to it as I. Mathematically, this is no problem, but we're just not going to be dealing with those types of problems in this course. So for us in that situation, because we're working over real numbers, we don't want things with i's. If this is negative, we say the polynomial is irreducible and you cannot factor it anymore. You cannot get a more general solution. So for example, let's say we have this polynomial. We could isolate for the x by moving the 1 over and then taking the square root of everything. But if I did that, plus minus -1, the solutions I'm getting are complex numbers. I'm getting things with i's. Okay, so for our case, we don't consider those. So we would say that this polynomial is irreducible. But another way you could do it is if you put it into the quadratic equation. Notice that the thing under the root here, I end up getting -4. Because it's less than 0, there's no solutions in the reals, the polynomial is irreducible. And here's some nice factorization rules. We have the difference of squares, which is if you have no, I almost said crosshairs. If you have no cross terms, so things with x and y, I just have an x squared, a y squared, and I have a minus or a plus. I can factor this immediately like this. So same factoring except one of the terms is minus, one of them is plus. Perfect square is when you have x plus y squared, and when you expand it, it'll look something like this. If you have cubic functions without cross terms, so I don't have things like x squared y or y squared x, but I only have an x cubed y cubed, if you have a minus, you can immediately factor it this way. And this part here is irreducible. I can't simplify it anymore. Okay, if you have the sum of cubes, so instead of having a minus here, you have a plus, you can rewrite this like this, where again, this is irreducible. I can't simplify it anymore. Okay, so let's say just for an example, we have this cubic polynomial where I only have a constant term and I only have a cubic term. It may be a little bit hard to see that this is a difference in cubes because you would have to more think about the problem as 2x all cubed minus 1 cubed. So in that formula that we saw, this whole thing here would be like the x, and this thing all here would be like the y. So remember that formula said that you would have x minus y. In our case, it would actually be 2x. And then you would have your x squared plus xy plus y squared. Okay, so our x squared in this case is our 2x, so I get 4x squared, 2x times 1, which is just 2x, and then 1 squared, which is just 1. Okay, and to convince ourselves, to prove to ourselves that that second polynomial is irreducible, if you try to plug this into the quadratic equation, I end up getting a negative under my root. Okay, so I can't simplify it anymore. So I can factor the polynomial to give me this. Okay, so I apologize that that wasn't a little bit longer, more detailed. I didn't write out all the solutions, mostly just because I want to get this out to you today. And I've been recording for a long time without a microphone, so I apologize. Anyway, I hope this is helpful, and I will see and talk to you soon. Bye.